Imagine you're scrolling through a short video app, and the recommendation engine has to decide in milliseconds what to show you next. To make that decision well, it ideally wants to look at everything you've ever done on the platform. Every video you watched, every ad you clicked, every product you bought. That history can stretch to tens of thousands of interactions. But running a transformer over a sequence that long, for every candidate item, for billions of users, is computationally brutal. So how do you actually do it in production? That's the problem the longer paper from ByteDance tackles head-on. To understand what's new here, it helps to know how the industry has been coping. The dominant trick is two-stage retrieval, used in systems like Sim and Twin. The idea is to first scan your massive history and pull out maybe the 100 or so items most relevant to the current candidate, then feed only those into a normal short sequence model. It's like skimming a 1,000-page diary for entries that mention coffee before deciding whether to recommend a new espresso machine. The problem is that the retrieval stage and the ranking stage are trained separately, so they disagree about what matters. Other approaches pre-train a single user embedding from the long sequence, but that compression throws away detail. And memory-augmented models like MIMN and MARM cache intermediate computations, which helps efficiency but still doesn't let the ranking model see the raw sequence directly. All of these are workarounds. What ByteDance wants is true end-to-end modeling, where the ranking model itself attends over your full 10,000 item history. The core challenge is that attention scales quadratically with sequence length. If your sequence has 2,000 tokens and each token is a 32-dimensional embedding, you're already in expensive territory. Longest first move is what they call token merge. They take groups of adjacent items in the history, say groups of 4 or 8, and compress each group into a single token. Think of it as zooming out on your history. Instead of looking at every individual frame, you summarize chunks of recent behavior into one compact representation. This shortens a sequence by a factor of 4 or 8, which dramatically cuts the attention cost. But naive concatenation of items within a group loses fine-grained detail, so they apply a tiny transformer they call InnerTrans inside each group, letting the items in a group interact before being merged. Because the group size and embedding dimension are both small, this InnerTransformer is cheap, but it preserves the local texture of behavior that pure concatenation would flatten out. The second key idea is global tokens. These are special tokens prepended to the sequence that represent things like the candidate item, the user identifier, and learned summary tokens. They have full attention over the whole sequence and everything attends back to them. They serve two purposes. First, they're anchors, where information from across the long history gets aggregated and where candidate-specific signal can interact with user history. Second, they stabilize attention. There's a known pathology in long-context transformers called attention sink, where deep layers obsessively focus on the first few tokens for no good reason. By giving the model dedicated global anchor tokens, the attention has somewhere meaningful to land, and the deeper structure stays healthy. Then comes the hybrid attention design. The first layer is cross-attention, a small set of query tokens, the global tokens plus the most recent 100 or so behavior tokens, attends across the entire compressed sequence. This is the compression step that pulls the long history down into a manageable representation. After that, several self-attention layers operate just on this compressed set, learning higher-order interactions. One subtle but important detail, they tried different ways to choose those query tokens. Learnable queries like in-perceiver or Q-former, uniform sampling, or just taking the most recent items. And the most recent items won clearly. That makes intuitive sense for recommendations, where recency carries strong signal. They also found that sampling about 40% of the full sequence retained 95% of the performance gain, which is the kind of marginal return curve that makes industrial deployment feasible. On the engineering side, the paper goes deeper than most academic work. They built a fully synchronous training and serving framework where both dense and sparse parameters live on GPU machines, eliminating the traditional parameter server bottleneck. Embedding tables are tiered: hot features in GPU high bandwidth memory, warm ones in CPU RAM, cold ones on SSD. They use mixed precision training with BF16 or FP16, which gave them 18% more throughput and 16% less training time. They aggressively recompute activations during backprop instead of storing them, trading compute for memory. And for inference, they exploit a key structural property. The causal mask is designed so the user sequence never attends to the candidate item, only the other way around. This means the key and value projections for the user history can be computed once and cached, and only the candidate's global token needs fresh attention, computation for each candidate scored. That single optimization took serving throughput degradation from -40% down to -6.8%, which is the difference between deployable and not. The results back up the design. On a 5.2 billion sample dataset from Douyan's ad system, Longer beats a vanilla transformer baseline by about 0.21% AUC, which sounds tiny, but in industrial ad ranking is a substantial lift. More interestingly, they validate scaling laws. Performance follows clean power law curves as you increase sequence length, parameter count, or compute, with R-squared values above 0.96. So this isn't just a one-off architecture. It behaves the way large language models do under scaling, which is exactly what you want for a system you plan to keep growing. In online A/B tests, the live streaming ad format saw advertiser value lift by 1.17%, short video ads by 2.13%. On the e-commerce side, gross merchandise value per user lifted by 6.5% for live streaming and 5.3% for short video. Those are enormous numbers at ByteDance's scale. Now the honest limitations. The paper doesn't deeply discuss what happens when user histories are heterogeneous across very different surfaces, ads versus e-commerce versus organic video, and whether one unified model handles that gracefully or whether you need per-domain variants. The token merge strategy assumes adjacent items belong together semantically, which is true temporally but might blur across context switches in a user's session. The learnable query result being worse than just taking recent items is a little suspicious. It might indicate the learnable queries were undertrained or poorly initialized rather than fundamentally inferior. And while the scaling curves look clean in the tested range, the paper doesn't push to where they break down, so we don't know where the architecture's real ceiling is. Now let's walk through some questions you might have after hearing all of this. First, why does token merge actually preserve useful information rather than just blurring everything together? The key is that token merge is paired with InnerTrans, the small transformer that runs inside each group before merging. So within a group of, say, 8 adjacent behaviors, the items interact and produce a representation that captures their joint meaning, not just an average. It's closer to writing a one-sentence summary of a paragraph than to taking the mean of the words. And because groups are temporally local, the items inside a group genuinely tend to be related. They're often part of the same browsing session or interest burst. Second, why is the KV cache trick so effective here when it's already standard in language model serving? The reason it's a bigger deal in recommenders is that you're scoring hundreds or thousands of candidate items per user request, and each candidate would otherwise trigger a full pass over the user's 10,000 item history. By caching the user-side keys and values once and reusing them for every candidate, you turn what would be 1,000 expensive forward passes into one expensive pass plus 1,000 cheap candidate-specific attention computations. The causal mask design, where the sequence can't see the candidate, is what makes this caching mathematically valid. Without that asymmetry, the cache would be invalid because the user representation would depend on which candidate you're scoring. Third, what makes choosing the most recent items as queries beat learnable queries? given that learnable queries work well in perceiver and Q-former? The difference is signal density. In vision or general language tasks, learnable queries discover useful summary directions because the input is uniformly rich. In recommendations, recency is a known, extremely strong prior. What you did 5 minutes ago is far more predictive than what you did 6 months ago. Recent items essentially give you a free, high-quality initialization that learnable queries would need a lot of data to match, and even then they're starting from random, while recent items start from genuinely informative signal. For large-scale recommendation systems serving hundreds of millions of users, the most directly applicable lesson here is the KV cache serving pattern combined with the causal mask design. If you're building a ranking model that attends over user history, structuring your attention so that history never depends on the candidate unlocks massive serving efficiency, and you should design the mask that way from day one. The token merge plus InnerTrans pattern is also worth borrowing for any team currently doing two-stage retrieval. It gives you a path to end-to-end long sequence modeling without quadratic blowup, and the scaling laws suggest you'll keep getting wins as you push sequence length up. The other practical takeaway is the unified GPU storage architecture. Many production recommenders still split dense computation on GPUs from sparse embedding lookups on parameter servers, which creates network bottlenecks and gradient staleness. ByteDance's choice to collocate everything on GPU with tiered memory, hot embeddings in HBM, warm in RAM, cold on SSD, is the kind of infrastructure investment that pays compounding dividends as models scale. If you're planning a multi-year roadmap for ranking infrastructure, this paper is a strong argument that the future is fully synchronous GPU-native training and serving, and the sooner you start migrating, the sooner sequence length scaling stops being your bottleneck.